This is our third time of online lecture for nuclear reactor kinetics and control. So let's first review what we studied last time. So we are currently talking about chapter 5, reactor kinetics, and we talked about starting from neutron balance equations, we derived the equation for prompt neutrons without properly considering the effect of delayed neutrons. And after that, we introduced this concept of delayed neutrons. So this fit table 5.1 gives us some important nuclear data related to delayed neutrons, such as delayed neutron fractions. So for three different types of fissile material, uranium-233, uranium-235, and plutonium-239, we usually, of course, there are hundreds of fissile fission fragments that are able to emit neutrons. And those neutron emitting fission fragments are called as are called as precursors. And usually there are many such precursors, but we usually divide them into 6 groups depending on their half-lives. So we can see the 6 groups of precursors here. And these are the fractions related, those fractions, delayed neutron fractions associated with the half-lives of 6 groups. So if we see, these are the beta values. So in case of uranium-235, the total fraction of delayed neutrons would be less than 0.1%. So actually it is 0.65%. But this beta value for uranium-235 is, of course, greater than those beta values for uranium-233 and plutonium-239. So that means, of course, as you may realize that, so uranium-235 is the kind of a fissile material that most facilitate the control of reactor power. That means when we utilize uranium-235, controlling the power of a nuclear reactor would be the easiest compared to other two types of fissile materials. That means controlling reactor power with plutonium-239 fuel would be, of course, somewhat difficult compared to the case of uranium-235. So these were some basic quantities related to delayed neutron fractions, and we derived kinetic equations. So starting from here, if we briefly review the kinetic equations with consideration of delayed neutrons, so the change of neutron population is given by the source term, the external neutron source, and the prompt fission neutrons. And this would be the fraction, the delayed neutrons. So usually delayed neutrons are produced from the decay of precursors. When precursors decay, they emit neutrons, and they are sources of those delayed neutrons. Of course, this summation should be performed from I equals 2 to I becomes 6, because we usually divide such precursors into 6 groups. And then, of course, the change of neutron population is affected by the absorption of neutron and the leakage of the neutron when the neutrons leak out of the reactor. And so we now have just one differential equation. And there are 6 more differential equations. So basically, the left-hand side tells us the concentration of precursors, the ith precursor. Of course, we have 6 I stems from, so as you can see here, I stems from 1 to 6. So the change of precursor concentration is given by, this would be, so these are sigma f and average speed and neutron density. This would be the fission rate. If we multiply nu, we are going to get the average number of neutrons emitted per due to fission reactions, and beta is the fraction of delayed neutrons for ith group. And of course, this would be the decay rate. So this would be the production rate of the precursor, and this would be the decay rate of the precursor in ith group. So we now have 7 simultaneous differential equations. Of course, we need to solve them simultaneously. And of course, here we are able to find some steady-state solution for NT, the neutron density, and CITs. That's the concentration of 6 precursors, so 6 precursor groups. And we introduced the concept of reactivity. So by introducing reactivity, so by defining reactivity as K minus 1 over K, and also we introduced this new quantity called the prompt generation time. So now the same equation is now rewritten in a slightly different form by using the reactivity and prompt generation time. So in fact, if we move one in the previous page, so equations 5.40 and 5.41, that means that 6 simultaneous differential equations is now simply changed their forms to equations 5.47 and 48. So by introducing rho and capital lambda, we simply changed the form of simultaneous differential equations. So from now on, all we need to do is to simultaneously solve that equation. So how can you do that? So so we basically assume that neutron density will have exponential form of solution. So NT is assumed to be a exponential omega t. And also CITs the concentration of precursors will be assumed to have the exponential form with the same omega with that of neutron population. So the 7 simultaneous differential equations they are now reduced to just one equation. So in the left-hand side, we have the reactivity. The right-hand side, we have omega and all other parameters such as prompt generation time, beta I, and lambda i's. They are all constants. So this is just the equation between omega, rho, reactivity, and omega. Omega is closely related to the reactor period. So that means if 1 is given, so usually when reactivity is given, when reactivity is specified, then omega can be determined. And this figure 5.3 tells us how such omegas are specified. So simply the right-hand side is drawn in this graph, and then maybe the same way we can. So this is the line of omega, rho, the reactivity. So when reactivity is 0, then omega would be 0. What does that mean, omega would be 0? That means we do not have any change in reactor power. As the reactor power increases, as the reactivity is increased, so if we add positive reactivity, then we have solutions for omega. So how many? 1, 2, 3, 4, 5, 6, and 7. We are going to have 7 omegas that satisfy equation 5.53. And of course, all 7 omegas will be valid solutions. So because of that, all 7 omegas will be valid. So the neutron population is given as the sum of some constants multiplied with omega of exponential omega it. And of course, when we have 7 omegas, then we first sort the omegas according to their magnitude. So omega 1 is usually defined or denoted as the omega with the biggest magnitude, not magnitude, the biggest value. So the biggest one would be denoted as omega 1, and the smallest one will be denoted as omega 7. So in this case, from the biggest one, this one would be omega 1. In figure 5.3, this would be omega 1, omega 2, 3, 4, 5, 6, and 7. So when omega 1 is positive, as the case in this figure with this red line, then all other omegas, so there would be only one positive omega, and all the remaining 6 omegas will be negative. That means as time, because we have the form of exponential omega t, omega it, all other exponential, all the omega it's, when omega i's are negative, then they will gradually decay out as t increases. In that case, only only the first omega, the omega 1, in other words, omega 1 will dominate the sum of six terms. So, as in equation 5.55, the neutron density can be given as A1 exponential, in fact, omega 1t. That means the magnitude is basically governed by the biggest omega, omega 1. So inverse of omega will be defined as reactor period. What if omega is we are going to deal with negative reactivity, like this case? So still, we are going to have 1, 2, 3, 4, 5, 6, and 7 omegas that satisfy equation 5.53. The only difference is that in this case, now omega 1 is a negative value. And of course, we have 6 more omegas whose values are much smaller than omega 1. So of course, in this case, it has negative value. These omegas have negative value whose magnitude is, so in terms of magnitude, this omega would have the biggest magnitude. So that means if we take exponential omega t, this one decays out first. And after that, these terms. So of course, nt will be given as the sum of exponential terms. And only this sum is also governed by the omega 1, which has the biggest value. So in terms of magnitude, omega 1, the magnitude of omega 1 would be the smallest. So because when we deal with exponential minus omega t, in that case, the one which governs the overall solution will be the exponential function with the smallest omega. I mean, not the omega with the smallest magnitude. So in either case, no matter omega is positive or omega is negative, this solution is mainly governed by the biggest omega, no matter whether omega 1 is positive or negative. So the overall solution can be approximated. Instead of summing all 7 exponential terms, the overall solution can be approximated with as a1 exponential omega 1t. And if we define 1 over omega 1 as reactor period, then of course the equation will be given as exponential t over reactor period. So this is what we have studied last time. Okay. So these are the kinetic equations. In section 5.5, we derived this in our equation. And of course, the exact solution will be sum of all 7 exponential terms. And all the seven omega i's will be given from this in our equation. But as I explained, the overall solution, as t increases, the overall solution is governed by the biggest omega, the omega 1. And this will be rewritten as a1 exponential t over reactor period. So we define reactor period as 1 over omega 1. 1 over the biggest omega. So this is what we studied last time. So, and so I also want to emphasize that the equation 5.45 is valid for both negative and positive reactivities. And so when I talk about this equation in our equation, then it is the relation between reactivity, and because 1 over omega is reactor period, so this is the relation between reactivity and reactor period. So if we decide reactivity, then reactor period can be determined. So a plot of rho reactivity versus T reactor period must be constructed. So that is equation 5. That is the figure 5.4 in our next page. So it is also important to clearly understand this figure. This is the figure relating the reactivity and reactor period. So that means if the reactivity is given and reactivity is determined, then reactor period can be determined. And these values are the capital lambda, prompt generation time. So the relation reactor period is determined by the magnitude of prompt generation time. So how can you determine that? So the way how to draw this figure can be, of course, is also given in this relation. So when rho is given, and we are able to find solution for omega. So especially the biggest omega, omega 1. So when we find the biggest omega, omega 1, then by taking the inverse of omega 1, we are able to calculate the reactor period when all other parameters are given. So beta I, lambda I, they are all the quantities, physical quantities that are already fixed and provided in table 5.1. So table 5.1 here. So in case of uranium 235, we have half-lives corresponding to the 6 groups and beta i's for the 6 groups. And this would be the beta, the sum of beta i's. So if we go back to in our equation, so beta i's, lambda i's can be, these are given in table 5.1. Prompt generation time, it is, so the overall equation between reactivity and reactor period is also affected by the magnitude of prompt generation time. So that is what we can observe in figure 5.4. So if we go to the figure 5.4, then what we can see is that these graphs are all, or the relation between reactivity and Richter period is affected by prompt generation time. So, so we may so if I show you an example, we are able to write this kind of MATLAB program, and by using that, the solution, so it is still calculating. Oh, here. So we now have this solution here. So this is the result that is just calculated from the MATLAB program that I just showed you. So, what is the point of this curve, this graph, or what can you learn from this graph? So, so first thing that we should see here is that when the reactivity approaches 0.0065, that is the value of beta for uranium-235. So when the reactivity reaches that value, beta, then prompt critical is achieved. So what is prompt critical? That is this is the critical condition when this is the situation when the criticality is maintained only with prompt neutrons. So in such case, so from this time point, so what we can see is that when the prompt generation time is the smallest case, then so from this time point, the Richter period decreases very, very rapidly as we slightly increase the reactivity from this time point on. That means if Richter period is small, if the Richter period is small, then the exponential function increases very rapidly. So if the Richter period changes from, in this case, from 0.1 second, this is already very rapid change. But from this on, if the reactivity changes slightly more, slightly higher, then the Richter period changes to 10 to the power minus 4 seconds. So in 1 second, the reactor power can, so for example, if the reactor period is 10 to the power minus 4, that means in 1 second, Richter power may increase to the exponential to the power 10,000. That is, of course, a huge number. So if the reactor power changes that rapidly, it is very hard to properly control the reactor. So of course, as always, the avoiding such prompt criticality is very important in controlling nuclear reactor. And also, this condition of prompt criticality. So when this is, of course, when in the case of uranium-235, this is the case when the reactivity reaches 0.0065. The delayed neutron fraction of uranium-235. So to indicate how close the reactivity reaches prompt criticality, so I'm currently talking about the prompt criticality in page 129. And as a measure how close the reactivity, so as a measure how close a reactivity reaches this prompt criticality, we introduce the reactivity in terms of, sometimes reactivity is given in terms of dollars. So $1 indicate that the reactivity just reached prompt critical. So $0.1 that will be equivalent to 10 cents. So that means the reactivity reaches 0.1 or 10% of the prompt criticality reactivity. That is, we have 0.00065. So if we introduce, so when we talk about prompt critical, so prompt criticality, so nuclear fission reactions. Mainly governed, mainly caused, mainly induced by prompt neutrons. So we are going to introduce $1 equals is given as rho the fraction of reactivity in terms of where's beta, the delayed neutron fraction. So of course, for uranium-235, beta equals beta equals 0.0065. If reactivity is given as $0.1, that will be equivalent to 10 cents. that will be same with 0.00065. Maybe I need to delete this if. So $0.1 or 10 cents. So of course, $0.1 is equivalent to 10 cents. And 10 cents in reactivity means this amount of reactivity. So previously, in my last lecture, I also told you that in nuclear reactor, we use this magnitude unit of 10 to the power minus 5. And this is usually, this magnitude, 10 to the power minus 5, is usually written as PCM. So this unit PCM is the one that is widely used in nuclear reactors. I mean, in the field of nuclear reactor control. So when you visit a nuclear power plant, then you may see that when the senior reactor operator and reactor operator communicate to each other, then they may use this unit of PCM. And so when we move to, there's one more thing before we proceed. So when reactivities have a negative value, there is some asymptotic limit to how fast the neutron population can be decreased. So for that, we need to move on to figure 5.3. So when we see this part of the graph, then it increases, it continuously increases. That means if we increase the reactivity, then the reactor period, omega 1, will gradually increase. That means the reactor period will gradually decrease. However, when we decrease the reactivity, even though we decrease the reactivity to a very small negative value, but when we see the graph, then there is some asymptotic limit that omega 1, the asymptotic limit is that omega 1 will not be smaller than negative minus 1, negative lambda 1. So that means omega 1 may approach, omega 1 gradually approaches to minus lambda 1. So the omega 1, the smallest value of omega 1 can be negative lambda, smallest value of omega 1 can be negative lambda 1. And that is, in case of negative reactivity in here, even though we gradually decrease the reactivity, but there is some limit in the omega 1 value. That is some limit. In other words, there is some minimum value that omega 1 may take. That is negative lambda 1. So what does that mean? So for negative reactivities, so maybe we may move to our notebook. So for negative, instead of writing that, instead for negative reactivity, smaller than 1, reactivity smaller than 1, then what we can see is that omega 1 approaches negative lambda 1. Negative lambda 1. This means reactor period approaches 1 over lambda. So how can you calculate the 1 over lambda? 1 over lambda is the lambda corresponding to the biggest half-life. So lambda 1 corresponds to 0.693. That is actually natural log of 2 over half-life, the biggest half-life. So this means half-life, maximum half-life, and divided by 0.693. And now we may recognize that there is some typo in our textbook. So in this explanation, it should be T half-life max divided by, so this 0.693 should be placed in denominator, not numerator, as we can see in this equation. So this is approximately 56 seconds. You may confirm this in table 5.1. The biggest half-life in the table is 56 seconds. So this would be approximately 80 seconds. So when for negative reactivity, we have some asymptotic reactor period. That means the reactor period gradually decreases as reactivity decreases, but reactor period approaches to this value of 80 seconds. So we have not learned the chapter 7 of Lamarck's introduction to nuclear engineering. So in chapter 7, so this is Lamarck and Boretta's introduction to nuclear engineering, the third edition. And you are able to see a very similar equations here. But in this case, it is simplified with only two groups of delayed neutrons. And here, it is given that this is the case when we have the delayed neutrons with 6 groups. So this is general reactivity equation. This is the in-hour equation that we could see in our current textbook. And with this somewhat simplified approach, what we can see is that in case of a positive reactivity, as reactivity increases, reactor period gradually decreases. And this is the case when the prompt criticality is achieved. So here LP corresponds to prompt generation time, and as the reactivity, when reactivity approaches to prompt critical, then suddenly reactor period suddenly decreases to a very, very small value. And when we deal with the negative reactivity, as the magnitude of negative reactivity increases, that means as the reactivity decreases, then the reactor period gradually decreases. But instead of continuously decrease to smaller and smaller value, there is some asymptotic reactor period, and this value approaches to 80 seconds. That is the one that we just calculated. So this is what we can also see in Lamarck's introduction to nuclear engineering. So let's go back to our textbook. So this t-value, asymptotic t-value, is in fact almost 80 seconds. So the next case, again, we are going to go back to figure 5.4. So here what we can observe is that in this region, when reactivity is not that big, in other words, when reactivity is small, then the reactor period is not significantly affected by the prompt generation time. So the question is, whether we can derive the kind of specific relation for this case when reactivity is very small. So when reactivity is very small, when the reactivity is small, reactivity TBT is small. In other words, when reactivity is very, very small. Reactivity is how small? Instead of 1, maybe reactivity is smaller than like 0.01. So I cannot write 1 here because 0.1 or 0.01 is still a huge magnitude in the world of reactivity. So instead of just, so let me erase this part. So when reactivity is very, very small, if we go back to our textbook, this is the case when reactivity is like less than 0.002. So in this region, so can we derive some relation for the case when reactivity is very small? So we should start from in our equation. There is something missing here. So omega, we miss omega here. Okay, we may say that so I just deleted this relation, but I'm going to rewrite this. So when reactivity, so when we compare this denominator, so reactivity is very small such that they are relatively very small compared to lambda i's. Of course, lambda i's are the inverse of, natural log of 2 over half-lives of the 6 precursor groups. And in that case, if the reactivity is this small, then so this omega is much smaller than lambda i's. That means we are going to omega. So maybe this relation needs some more explanation. So when we go back to figure 5.3, Here, what we can see is that the relation between, so kind of we are able to see some kind of linear relation between omega, between reactivity and the calculated omegas as the biggest omega, omega 1 as the biggest omegas, as the biggest one among 7 omegas. So with that, linear relation in mind, so when the reactivity is small, then omegas, the omega 1, will be also very small. It will very close to 0 because we could see the linear relation between omega and reactivity. So if we go back once again, so if reactivity approaches to 0, then also this omega will approach 0. So when reactivity is small, then, so the general rule is that when reactivity is small, omega will be also very small. So because of that, omega 1, so if omega 1 is very small compared to lambda I, so I'm sorry, maybe I need to fix this. Instead of omega, this one should be, instead of omega, this one should be omega 1. So when omega 1, so when the reactivity is small, very small, such that omega 1, the solution of the in-hour equation, the biggest solution from the in-hour equation, is smaller than lambda i's, then we may ignore this part. So, of course, this means that omega plus lambda I can be approximated. This can be approximated with simply lambda i's. So here, this is approximated with beta I over lambda i's. And what is this? Sum of beta i's over lambda I. So this one requires page 123. So we need to go back to 123. So if we move beta to the left-hand side, what we can see, this is the equation for calculating average decay constant. What we can see is the beta I over lambda I, sum of beta I over lambda I equals beta over lambda. As far as this average decay constant was already calculated. Of course, also, it's not difficult to calculate this. So, going back, So now we know that this is simply beta over the sum of this is beta over lambda. Beta over lambda. And also, previously we also calculated that when was it? So page 124. So when we compare prompt generation time and beta over lambda, in fact, prompt generation time was defined as L over K. That's equation 5.46. So this was the definition of prompt generation time, L over K. And if K is very close to 1, then in that case, the prompt generation time is very close to this L. And also, last time it is emphasized that beta over lambda is much bigger than neutron lifetime, L. So the point is that beta over lambda is normally much greater than prompt generation time. So that means this can be ignored when this is compared. So maybe I need to place approximation here. It is approximated, and also it is approximated that this can be ignored compared to beta over lambda. Or we can say that prompt generation time plus beta over lambda can be approximated as beta over lambda. And we are going to multiply omega here. So what does this mean? Then, of course, the Rita period should be calculated. And this, if this becomes 1 over t, if this one equals 1 over t, of course, omega 1 will also satisfy this relation. So this one becomes over t. So now t should be same. T should be same with beta over lambda and rho and lambda. So this is equation 5.57. So we can see some linear relation. Not linear. 1 over. So when the reactivity is given, then we are able to see some inversely proportional relation between the reactivity and reactor period. And also, another thing is that this prompt generation time does not have any effect, does not have a significant effect on the result of the reactor period. So if we go back to figure 5.4, so when reactivity is very small, first the effect of prompt generation time disappear, and this curve almost follows the, so here the reactivity, the reactor period is inversely proportional to reactivity. So that's equation, that is the relation given by 5.57. So some explanations. Some explanation is that when for small reactivities, no matter the reactivity is positive or negative, reactor period, this T, is governed almost completely by delayed neutron properties, beta and lambda. And of course, the property of prompt neutron, this prompt generation time, its effect is almost disappeared. And another extreme is that above prompt critical. So this time we are going to look at here. Above, so this is the reactivity corresponding to prompt criticality, and above prompt critical. So in this reason, so above prompt critical, that means, once again, if we go back here, then of course above prompt critical, then omega 1 will be very, very large. Very, very large compared to all lambda i's. So omega 1, so above prompt critical. So above prompt critical. Omega or omega 1 will be much, much bigger than all lambda i's. So from this original equation, what can you learn? So omega will be much bigger than lambda i's. The sum of two may be governed by, the sum of two may be governed by, so this is approximated, and this would be mainly governed by omega. Then what happens? This one equals, so what will be remaining is that prompt generation time multiplied with omega plus, in fact, we are going to have, so these two omegas, this omega in the denominator will disappear by being cancelled with the omega out of the parentheses. And now, what is this? Sum of all beta i's. Sum of all beta i's are simply beta. So, of course, this one corresponds to the inverse of Ricta period. So the relation will be something like this. So the Ricta period is given as rho rho minus beta so prompt generation time over rho minus beta. So of course we are currently talking about the reason above prompt criticality. So in this region, the delayed neutrons will not have a significant contribution. So all the fission reactions are governed by prompt neutrons. So we have a what is that? The Ricta period is mainly governed by or being even proportional to prompt generation time over what is this value? Reactivity minus beta. So if we go back to the figure, so if reactivity is this value, then the difference between this dotted line and this reactivity is rho minus beta. So the distance from the prompt criticality also provides very important effect to Ricta period. And also what we can observe here is that as the prompt generation time decreases by a factor of 10, then also the Ricta period also decreases by a factor of 10. So the Ricta period is basically proportional to prompt generation time. So prompt generation time provides a significant effect in the region above prompt criticality. So maybe at this point, it is already 4:15. So we are going to have a short break until 4:30. And also, I would like to do some attendance check at this point. So I would like to ask all students to leave their name in the chatting window and then take a 15-minute break from now on. So we, from in our equation, today we actually, we have seen how Ricta period can be calculated for given reactivities. So let's first see. So this figure 5.4 gives us the general relation of reactor period for given reactivities. So we can see different curves for different prompt generation time. Now, as in our textbook, we also reviewed and tried to simplify in our equation for two extreme cases. The first one is when the reactivities are very small. So when the reactivity is small, then the relation between reactivity and reactor period could be simplified as can be seen in equation 5.57. Also, when above prompt critical, in other words, when the reactivity is very high. So when reactivity is very high, then we could derive the relation between reactivity and reactor period. And between the two extreme cases, of course, in this area, between reactivity is not very small or not very big. So in these cases, of course, the solution should be found numerically for a given reactivity to calculate or to find out the reactor period for a given prompt generation time. So from now on, we are going to talk about prompt jump approximation. Prompt jump approximation. In fact, this can also be found in figure 5.2. So that is what page 127. So when plus minus 0.1 beta, in fact, now we can see that the magnitude of reactivity is 0.1 dollar or 10 cents. So in the very early duration of the neutron population change, we can see that neutron population suddenly increases and approaches to some value. And then it follows exponential distribution. And this was called as a prompt jump. So here, this is called as a prompt jump. And then exponential growth or exponential decay follows these prompt jumps. And we are going to analyze the magnitude of a prompt jump given the parameters and how it can be utilized to measure reactor parameters. So once again, so we are going to see in figure 5.5, in fact, the situation is exactly the same. We inserted plus minus 0.1 beta over reactivity, and we can see that the reactor power suddenly increased. Neutron population compared to its steady state value, it suddenly increases about 10%. You can see about 10% increase in neutron population. And after that, it is going to follow exponential growth or exponential decay. And we would like to know the magnitude of this prompt jump. So, but from this figure, what can be seen is that the magnitude of a prompt jump is approximately 0.1, which maybe by instance, or there must be some theoretical background, but which corresponds to 0.1 beta reactivity. So there must be some relation between the inserted reactivity 0.1 beta and the magnitude 10% increase or 10% decrease in the magnitude of a prompt jump after the insertion of those reactivities. So this type of the magnitude of a prompt jump measurement is useful in experimentally measuring reactor parameters. And why do we see these types of a prompt jump? That is because the neutron population changes first, rapidly changes mainly due to by prompt neutrons, but the precursor concentration usually changes very slowly. And in this area, it can be seen that the precursor concentration is almost constant during that very short period of time. So, the basic theory behind the analysis, or the basic theory behind this constant neutron population is that due to the limited concentration, due to the constant concentration of precursors during very short period of time, the neutron population cannot increase so rapidly. So it is increased to some point and then maintain some value. So we are going to use this property to analyze the magnitude of prompt jumps. So here, so we can make use of this behavior, very slow change of precursor concentration compared to the change of neutron population. So we can make use of this behavior to estimate the magnitude of prompt jump. In the following two situations, rod drop and source jerk, we are going to see that basically these two situations are same, and the same equations will apply. So let's see the case of a rod drop. So suppose we have a source free, we do not have any external source, critical vector operating at steady state condition. That means by steady state condition, that means we are going to have steady state neutron population and also steady state concentrations of precursors. So in this case, the precursor concentration is given by this equation. And let's trace that. So in section 5.4, the kinetic equations were given with this equation. Yeah. The change of precursor concentration is given by beta I over prompt generation time, and nt minus lambda I ci. This is the decay rate of the precursors. And of course, the first term corresponds to the production rate of this type of precursor. And to talk about that, so we're going to case Rho drop case. And for steady state condition, this change of concentration will 0. And T, so let me write it for a steady state condition, for steady state reactor power, or the operating condition, reactor operating condition. There must be some steady state neutron population, and also all lambda i's. There must be some steady state precursor concentration. So with this equation, this can be changed like this, and therefore Ci is given as lambda I multiplied with neutron prompt generation time. So from the steady state condition, we are able to find out the steady state precursor concentrations. And one thing I need to note here is that load drop means that control load will be inserted into the reactor. That means the inserted reactivity will be negative. That means rho will be same with minus of its magnitude. It is simply to indicate that the reactivity is a negative value. So we are going to start from here in our equation. Not in our equation, from kinetic equation. So we do not have an external source let me also include that for a source free. That means ST equals 0. We do not have any external source. So we don't have this term. Instead of rho, we are going to use negative of the absolute value of rho, NT, and plus lambda I, and C instead of CIT, CI is now a steady state value. So instead of CIT, I'm going to insert this steady state value. That means lambda i's cancel cancels each other. And in fact, with respect to lambda I, with respect to I, this prompt generation time and steady state neutron population, they are all constant. So they can be taken out of this sigma. And we are going to have only beta I. So what will remain is a sum of beta I. So this one will be same with a negative minus of, so plus beta, and so what will remain is the sum over beta i's, which is the same with simply beta. That's equation 5.60. And we need to solve this differential equation. And of course, we are able to utilize the integrating factor. And I usually assumed that you all know how to apply that integrating factor to solve this differential equation. But maybe at least one time, instead of integrating factor, I would like to show you how to solve this differential equation. Maybe not using integrating factor, but simply by slightly changing this equation. So first, from here, we are going to have NT inside of this parenthesis. And we would like to also include this constant inside of this parenthesis. And in that case, what would it be? So both have prompt generation time in the denominator. So, and instead of minus, it should be, instead of plus, it should be minus. And so we should have this part in the denominator and beta and n0 in numerator. So dNTTT equals this. And because this part is simply a constant, we may rewrite this as, instead of nt, so dNTTT is in fact the same with, this is same with this. Because differentiating a constant with respect to t would simply 0. So this will be same with this. So what we can see is that because this is just one body, we may replace this with another function like pt or kt or anything. What can be seen is that differentiation of this function equals some minus some constant and the function itself. This is the major characteristic of a exponential distribution. So in fact, we are able to calculate the solution. Instead, it is going to have some exponential function, and this part will be the constant multiplied with t, and we should properly place the initial condition, the quantity at time 0. And of course, this would be same n0, and at time 0 will be same with n0. So with this, we will be able to find out let's see, if this would be n0, so when t equals 0, n0, 1 minus n0, 0, 1 minus n0, 0, 0 exponential minus t. When t equals 0, then both sides will be same. The initial condition is that when t equals 0, I'm slightly confused because this equation is not exactly same with the equation provided in our textbook, equation 5.61. So we have slightly different form of equations. So n0 when t equals 0, and t equals n0, 0, 0. So anyway, maybe we are going to check this later. So we should move this part to the right hand side. Plus, and then plus. And t equals 0. When t equals 0, and 0, this would be 1. And we are going to have n0 equals 0. Zero exponential minus. Yes, I found that the two equations are in fact same. Yes. So if we take n0, then this will be same with this. So if we take out n0 and 1 minus beta over absolute value of rho plus beta will be same with rho, absolute value of rho over absolute value of rho plus beta. So n0 is just taken out of the parentheses. So basically the equations. So this becomes equation 5.61. So I would like to show you at least one time how to solve this type of differential equation. You may apply integrating factor or you may follow the procedure that I just showed you to solve, to find the solution for the differential equation. So what you can see is that we have some initial value. Of course, this nt starts from n0. Starts from n0. And it approaches to some value. And then it gradually approaches to this value because this exponential term will disappear as t increases. So kind of the value, so as maybe we may go back to our textbook. So the textbook and this figure. So following the equation that we just derived, the neutron population gradually increases and it reaches some asymptotic value or steady state value that is given. So this value is given by only this part because the second term will gradually decrease as t increases. So the new steady state value, this value, if we assign n1 for this value, so this will be denoted as n1. Kind of a temporary, I'd like to say that for a very short time, the neutron population maintains this value. So the prompt, it is a kind of a prompt jump value. So suddenly increases and it reaches first to this value, n1. If we, in our textbook, so from n0, in a very short time, it reaches to this value. And then it follows exponential growth or exponential decay. So this n1, so the ratio between n1 and n0, in this case, 1.1 or 10% increase. Or if we go back, then this ratio if we move n0 to here, this would be the let me see. This would be the new value. And then yes, this is the case because this is the case of a rod drop when the reactivity is negative. So in that case, so if we inserted 0.1%, so as an example, if the inserted negativity, inserted reactivity, negative reactivity is 0.1 beta, then of course this would be 0.1 beta plus beta, beta over this. That means 1 over 1.1. One over 1.1. So that is very close to 10% decrease. When the inserted reactivity is, minus 0.1. So when we inserted the positive reactivity, then of course we need to solve the equation, but it is expected that we are going to see 10%, almost a 10% increase in the magnitude of prompt jump. And what about the case of source? So when we suddenly inserted the control rod and inserted 0.1 beta reactivity, then suddenly the reactor power decreases to here. And then after that, after this prompt jump, it follows the the exponential decay, as we can see in figure 5.2. That's page 127. So in this case, what we can see is that after 10% decrease in a very short time, that is called as prompt jump, and then exponential decay. Exponential decay follows when we inserted minus 0.1 beta. What about the case of 133? So source jerk. So we are going to see that the result is in fact same with the rod drop. So it is basically a subcritical reactor, and the amount of necessary reactivity that need to provide to make this reactor critical would be low. And this deficiency in reactivity is compensated by external neutron source, S0. So previously, we continuously studied that there are two cases for having time-independent solution for neutron population. The first one is critical reactor with no external source, and the second one is subcritical reactor with external source. And this is the second case. So we have an external source, and the reactor is in its subcritical condition. And it is a steady state condition. That means neutron population, precursor population, precursor concentrations, they all have time-independent solutions. and this would be the time independent or steady state precursor concentrations. So sudden removal, in other words, that is called as jerking, sudden removal of the external source, then the reactor is now subcritical with low amount of this negative value of reactivity. So this is exactly same, not exactly, this is almost the same with the case when we insert controllers with the negative reactivity role. So the first case, so load drop is the case for inserting a negative reactivity. This is the load drop case into a critical reactor. And this source jerk is the case of removing the source from a subcritical reactor. In both cases, there is this low amount of insufficient reactivity to make the reactor in critical condition. So the basic equations and the final results will be same for the case of source jerk. The load oscillation. So in this case, the reactivity gradually changes as a function of sign. And I'm sorry. In that case, so the equations may not be solved so simply. So here in equation 5.64, we only have the final results. So if sine omega t is averaged over time, then this omega term, sine term, will disappear, and the average over one cycle will be given with this equation. And if we plot the two ratio, then if we move n0 to the left hand side, then we are going to have only the right hand side. And then we will be able to determine the ratio between rho 0 over prompt generation time. So there's one more thing that I would like to add from Lamarche's book, is that so from Lamarche's Introduction to Nuclear Engineering, we have seen this curve. And then, so here we have this example of a power pulse. So control loads were ejected, and the worth of the control load was 2.72 beta. That is $2.72 of reactivity. It is much bigger than beta value, more than twice of the beta value. And what you can see is the reactor power suddenly rapidly increases, and it reaches to some maximum value and then decreases. and it also gave us the maximum power it recorded. Of course, theoretically, when we provide this amount of positive reactivity, then the reactor power should increase infinitely. But there must be some reason that this increase is limited by some other external factor. So of course later we are going to learn about that. So let's go back to our textbook. So what we have just studied. So thus far, our treatment of the time-dependent behavior of a chain reaction has not accounted for thermal feedback effects. So in that sense, such treatment is frequently referred to as zero power kinetics. So if power is generated, that heat will be generated and accumulated in the nuclear fuel, and then or in the nuclear fuel or in the coolant. So as the temperature of nuclear fuel increases, or as the temperature of the coolant increases, then the situation gradually will be changed. So by zero power, of course, it is assumed that power is increasing, but the amount of the magnitude of power is so small that it is basically assumed that the generated power do not have any effect on the temperature of fuel or coolant. Yes, so if the energy is created, then this energy is large enough to cause temperature of the system to rise. So power will increase temperature. Temperature will increase, temperature will decrease material density. If density decreases, then macroscopic cross-sections will decrease, because macroscopic cross-section let's prologue to reactor dynamics. So section 5.2, we have talked about zero power kinetics. So So the point is that when power increases, see, when power increases or P increases, well, P is big enough, then what will be happening? Temperature increases. The increased temperature will decrease, density will not increase, density will decrease. Then macroscopic cross sections. Sigma also decreases. So fission cross section will decrease. And also, of course, the absorption cross section possibly also decreases. So we may expect this chain reaction, and therefore they eventually affect the power, the reaction rate, fission reaction rate, and eventually affect reactor power. So if power significant, let's place this condition here. So if power generation is significant, also what other effects? We may expect Doppler broadening. This is the effect on resonance capture cross-section. And also, if we see the testable, then thermal reactors will also be hardened because Maxwell-Boltzmann distribution also has some dependency. So, what if Doppler broadening? So, by Doppler broadening, temperature increases and more neutrons will be absorbed, and eventually power will decrease. So we need to think about such feedback effect. So our textbook, next page. So it also talk about temperature in thermal reactor, temperature dependence of Maxwell-Boltzmann distribution. So usually this type of negative feedback is provided. Also, so if we consider all these feedback effects, then when we design a nuclear reactor, it must be made sure that under all operating conditions, this feedback is negative as the temperature increases. So this negative feedback. So maybe later we are going to quantify this feedback effect with some coefficient. So like field temperature coefficient indicate that as it indicates whether the overall feedback effect is positive or negative. If the coefficient is negative, then the feedback effect is negative. If it is positive, then the overall feedback effect provides a positive feedback to the Richter power as temperature increases. So we need to look at figure 5.6. So with the zero power kinetics, we do not consider feedback effect. So under that condition, as power increases, then the temperature, the neutron population will also increase, as is Richter power. But if we consider such negative feedback effect, then as power increases or a neutron population increases, there is some mechanism to gradually reduce that Richter power or neutron population, so that power or neutron population can be limited to under some value. So such negative feedback is very important in maintaining the safety of a nuclear reactor. So even if positive reactivity is provided, it gradually continue without feedback effect, the power will gradually increase. But with the negative feedback, of course, the power will gradually increase, but the increase rate will be somewhat limited. So as in this case, the power becomes larger, the curve with the feedback becomes concave downward and stabilizes at a compensated at constant power. So when the Richter power is stabilized to a steady state value, to a constant value, in that case, this negative feedback effect compensates the initial positive reactivity insertion. So such feedback effect will be dealt with in chapter 9. So in chapter 9, we shall take up reactivity feedback in more detail, and we are going to examine the interaction with the reactor kinetics to determine their transient behavior. So before moving to chapter 9, of course, we need to understand, as power increases, how the temperature of a field increases and how the temperature of coolant increases. So to understand that, on 199, so before moving to chapter 9, we first need to understand how energy produced by fission reaction, which is stored in the nuclear fuel, how such energy can be transported to coolant and then eventually to be utilized and transformed into mechanical energy and then electrical energy. So we are going to first review how energy is transported in this system, so that we are able to clearly understand how temperature changes as we increase the power. And that temperature of the fuel and temperature of the coolant will determine the feedback effect. And that feedback effect will also determine the final power, Richter power, that can be achieved after inserting some positive or negative reactivity. So we just finished the chapter 5. period. This would be 115. And control Alt, and then so in Lamarck's Introduction to Nuclear Engineering, this chapter 7 is all chapter 7 covers all the topics related to reactor kinetics and control. And here what I would like to show you is that the temperature of the fuel reacts immediately to changes in reactor power. So it is called how feedback effect is given related to the fuel temperature is called as a prompt temperature coefficient. And then the design requirement is that, so in the United States, that is the Nuclear Regulatory Commission, that is the regulatory body in the United States. And this regulatory body will not provide a license, will not allow any design that unless this feedback effect is negative. In other words, all licensed reactors, all the reactors allowed to be built in the United States and also in Korea also. Our regulatory body also imposes the same rule or same requirement for the design of nuclear reactors. And all licensed reactors are thereby assuring, we need to assure that all the fuel temperature coefficients or the feedback effect of fuel temperature. So fuel temperature provides negative feedback effect to the reactor power. And this negative feedback effect is mainly given by Doppler broadening. Because this fuel temperature direct or immediately, the reactor power immediately affect the fuel temperature, even though there is some time lapse between the time of power increase and the time when not the time that the coolant temperature is affected by the increased power. So I would like to briefly review what we just studied. 120, 100. So chapter 5 was about reactor kinetics. And first we derived the equation for prompt neutrons. And then also started to consider delayed neutron. And with consideration of delayed neutrons, we developed kinetic equations. Here, simultaneous equations, simultaneous differential equations. And then, by introducing the reactivity and prompt generation time, the simultaneous differential equations has this form. So as shown in figure equation 5.47 and 48. And then And then by assuming NT as a NT and CT, neutron population and precursor concentration as so by assuming that neutron population and precursor concentration follows an exponential function, we were able to derive this in our equation. So in our equation, is the relation, show us the relation between inserted reactivity and omega is directly related to the reactor period. And by solving, by numerically finding the solution, while for a given omega, for a given reactivity, so we could see the relation shown in figure 5.4. So this is the relation between reactivity and reactor period. So when reactivity is small, then we are going to, the relation becomes, when reactivity is small, very small, then the relation between reactor period and reactivity is given as shown in equation 5.57. Above the prompt criticality, the relation is given. The relation between reactivity and reactor period is given as in equation 5.58. In between, of course, we need to find numerical solution. And I just showed you that you are also, I hope that you are also able to find the exactly same curve, or say you are able to find solutions for a given prompt generation time and the reactivity, and also understand their relation. And then by looking at, of course, in figure 5.2, the characteristic of power change is that suddenly, so reactor power, after inserting positive or negative reactivity, reactor power suddenly increases or decreases to some level, and then follows exponential growth or exponential decay. So this change, sudden change, is called as prompt jump. And the magnitude of a prompt jump could be calculated by using the fact that the precursor concentrations do not change significantly in a very short time. And we are able to find the magnitude of prompt jump. And then if we know that, then think about this. So where do we use this prompt jump, or the equation for prompt jump magnitude? So if we do not know how effective control laws are, so-called, we do not know the worth of control laws, and then in that case we are able to experimentally determine the worth or the effectiveness of control laws. So by suddenly inserting the control laws, then the magnitude will suddenly decreases. And if we compare the two ratios, then we will be able to find out their worth or effectiveness. how such control laws affect the reactivity of the reactor. So this magnitude of rho can be experimentally measured by using this rod drop experiment. And the case of thrust jerk will be same. And I conclude this chapter by mentioning that currently we have not considered any feedback effect, but in chapter 9 we are going to include feedback effect in our analysis. So this is the end of chapter 5. Once again, well, this one, or in case of this is the Lamarck's Introduction to Nuclear Engineering. Yes. So previously, when I taught this reactivity and reactor period relation, I usually, so this would be the result of the analysis for that is very similar to the one shown in this section, this figure 7.2. This was given as a homework, usually, but I realized that a lot of students have difficulty in properly solving or finding these curves. So I would like to suggest that any students who are able to find these curves, or once again, this one, or still the material program tries to draw this curve. Okay. So any students who think he or she is able to draw this figure, and then I would like encourage you to challenge it to draw exactly the same curve like this one. And if you think you succeed in that, then please report me as you finish it. So maybe the kind of the challenge problem that I may suggest to all students in this course. So that is a kind of problem, homework problem that some students may challenge. So basically, the homework to you is that you need to read all the textbook in chapter 5. And then, so that reading assignment is your homework. And if you have any question, please ask me through email or by using eClass. So this would be end of today's lecture, and we just finished the chapter 5, and next time we are going to move on to another topic. So have a nice week, and then I'm going to see you next Monday.